All right, so we're going to continue on with Lewis structures, and I'm going to give you some. I'm going to give you one structure. We're going to do it together, and then we'll see how we do. So, in this case, I'm going to give you an ion. That will actually be a little bit something we haven't exactly covered. So, we're going to go through our rules again, just to practice using those. So the first rule is that we want to figure out the total number of electrons, and so I'm going to use my little table. Again, feel free to do it however you want. It is super important, though, that you have the right number of electrons. Now I'm going to put the charge here, and that's going to help me account for electrons. It's going to be, this is where one of the biggest reasons why making a table is helpful is for positive or negative charges. So this is the number of valence electrons. So nitrogen looking at the periodic table, 5 valence electrons. We have 1 nitrogen, so that gives me 5 electrons. For hydrogen, has 1 valence electron. We have 4 of them, so that gives me 4 valence electrons. And you'll notice in these Lewis structures, we very rarely have an odd number. If we have an odd number of valence electrons, or total number of electrons, it means we have a radical. Those aren't very common. We can find them for some nitrogen compounds. It is important to remember that if you end up with an odd number of total electrons, double check your math. Make sure you didn't make a mistake. That's often the case. The plus sign in this case means that you have 1 electron less than you would if it was a neutral compound. So the electron has been lost by a nitrogen or hydrogen, and so we would have 9 minus 1 is 8 electrons. Okay, so that's the total number that we need to match up with our structure. If we look at the number of bonds, again, anything that contains a hydrogen will not be the central atom. So nitrogen has 5 electrons. It needs 8, so it's kind of like 5 plus blank equals 8. So it needs 3 bonds. Hydrogen needs 1 bond. Again, won't be the central atom if you only need 1 bond, and then there's no bonds associated with a positive charge. So our central atom is nitrogen. So I'm going to take the nitrogen, and I'm going to connect the 4 hydrogens to it. That's my second step. Okay. Now I'm going to, and part of our second step, technically, this is our third step. Second step was to determine the central atom. So this is technically our third step. When we attach our hydrogen atoms, we're going to give every outer atom a full octet, or in the case of hydrogen, a duet. We already are good to go there, so we've done the third step just by connecting the hydrogens to the nitrogen. Okay, now we're going to count up the electrons and see if we have enough in our structure. So I'm going to count up 2, 4, 6, 8. So that's 8 electrons. That matches with what I need to have, so I can't add any more electrons to my structure. And next thing I'm going to do is I'm going to check to make sure. So that was me checking the total number. And then the fifth step is checking the central atom to make sure it has 8 electrons. So nitrogen has 2, 4, 6, 8. It has 8 electrons. So that's our structure. Now, the last thing, and this is something that a lot of students miss points on, is that for ions, for purposes of that we'll see in a sec, we need to put a bracket around ions and put the charge on the outside. And the reason is that we're going to be calculating the formal charge for atoms, and all the formal charges, which is a way of helping us determine the most stable structure when there are multiple kind of structures using multiple bonds, which we'll get to in a sec. Formal charges are used. All the formal charges of our structure add up to the total ionic charge that we see on the outside, and so we keep brackets there to separate the individual formal charges of the atoms and the total charge of the ion. That's why the bracket's there. You got to put the bracket every time you have an ion. It's very easy to forget. Sometimes I'll even forget it. So try your best as well. Okay, so let's do one more. I'm gonna do one more, and then I'm gonna give you some. So let's do O3 ozone. So it's a simple table that we're gonna do. So it's just oxygen, no charge. So if we look at the number of valence electrons, we have each oxygen comes with 6 valence electrons. We have 3 oxygens, so that gives us 18 electrons. that's all of our electrons, and so 18 is our total. Now the central atom, we have bonds. Each oxygen wants 2, but we have 3 oxygens, so we're just going to put the oxygen, we'll put oxygen in the center, and then the oxygen on the outside, obviously. And so we've done steps 1, the table, 2, determining the central atom, and now the third step is going to be attaching the atoms and giving the outer oxygens, those attached to the central atom, an octet. Now, I'm not going to give the central atom electrons yet. You first have to count electrons, and this is really important. So I'm going to do this, and I'm going to count electrons first to make sure I don't already have 18 electrons. If you start adding more electrons to the central atom, you might have a structure that ends up with more electrons than what you need, and then you get into an issue because you don't know where to take away those electrons. So if we count, let's count the electrons. We have 2, 4, 6, 8, 10, 12, 14, 16. So we have 16 electrons. And so I need to put 2 more electrons in, and so I'm going to do that, and the only place I can put them in is as lone pairs on the central atom, okay? So that's the fourth step, is to count electrons. Now the fifth step, you'll realize that, so now my structure has 18 electrons. And again, we'll just double check. 2, 4, 6, 8, 10, 12, 14, 16, 18. So we have 18 electrons. That's good, but you'll notice that this hydrogen, oh, check, I got a laser pointer. So this oxygen right here does not have, we need 2 more electrons, and so what we're going to do is I can't add another lone pair. If I add a lone pair, I'm going to have 20 electrons. That wouldn't match up with my number here. And so I need to take a set of electrons either from this oxygen to this oxygen. So I'm just going to say, okay, I'm going to make a double bond here. So I have, so if I do this, I get oxygen, lone pair, double bond, and then because I used one set of lone pair, I only have 2 left, and on this side, I have single bond, so I still have, that's not a single bond. Now it's a single bond. So if I look at my structure, I'm going to make sure I did this right. So first, does every oxygen have an octet? So on the left, I have an octet, 2, 4, 6, and then the bond makes 8. In the center, I have 3 bonds, that's 6, plus a lone pair is 8. And on the right side, I have 2 bonds, that's 4, and 2 lone pairs, that's 4 plus 4 is 8. Okay, so now we need to make sure that we have 18 total electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. So we still have 18 electrons. So that's still good. Okay, but you'll notice that our structure could have also taken 2 electrons from the other oxygen. And so we could have had this structure. And what I'm going to do is, I'm going to, erase all that, and then I'm going to draw the orange structure is what would happen if we did the orange arrow. This will kind of help color code things a little bit. Okay, so each arrow is showing each potential structure, and so you'll recognize that we have a little bit of resonance here. Now, you might say, hey, these structures are just, if you flip the top structure around, you get the bottom structure, and that's absolutely accurate. These are indistinguishable in any way if you have them in nature, but the point is, if I ask which one's real, the true answer is nothing is real. That's like that one surfer dude that says nothing is real, man. This is highlighting one of the big shortfalls of Lewis structures is it does a really poor job at resonance. Resonance is when you have structures that actually don't represent the real structure. So that is to say that because the double bond could be placed on either side of the electron, that neither one of these structures actually occurs. What really happens is that you have a structure that looks like this. It's an oxygen with a single bond. And then if you were to measure these, so the way we could tell the actual structure is I can go and measure the actual structure, and I can say that if we look at bonds, single bonds are the longest, double bonds shorter, triple bonds the shortest, and this has to do with overlap. So I can go and measure the bonds, or researchers can measure the bonds and say, okay, if these were two, if either one of these structures was real, I would expect that this bond would be shorter than this bond. Or I can say the bond length would be difference between the two oxygens. In actuality, this bond length, if we measure this one and this one, they are both the same length, and they are shorter than a single bond. Oh, single bond. But, whoa. Okay. But longer than a double bond. That is to say that, and I'm going to actually do one thing to make this look a little nicer. Oh. So that is to say that these bonds actually have characteristics of a single and double bond. So what's really occurring is that this double bond is flipping between the two oxygens, and that each of these bonds, if we were to measure them, actually are measuring like 1.5. That they have a length that's in between a double bond and a single bond, where a double bond would be shorter. And so this is actually not a resonance structure, because I can't, or Lewis dot structure, because I can't put, if the bond's flipping back and forth, I can't put electrons in places where we actually show the total number of electrons. And so we get around this by reporting both of these structures, where the double bond is in each location, and putting a double-sided arrow between the two. And if you have two potential places for the double bond, you have two structures, the arrow in between. If you have three, then you do three resonance structures. So just know that Lewis structures do not handle resonance structures well, and because of that, we have to draw all potential structures, understanding that the real structure is a hybrid between those structures. More on that in a sec. So let's go, and I'm going to give you a couple structures to do, and then the next video will be solving them. So let's have you do the following structures: SO3. Do SO3, and let's do, let's see, how about, we'll do PCl5. We'll do SO2, and let's see, and we'll do that for now. We'll do those three. So go ahead, do those structures. If there's resonance structures, show them, do all your steps, and then I'm going to go through these three structures in the next video.